Hello everyone. Today in this video, I will introduce how to make your own product with the features you want at a very low price. There are lots of electronic products in the market. But sometimes you wouldn't get the exact product of your needs. It can also be more expensive than you think. For this reason, it becomes necessary and handy when you can build your own PCB. The tool to be used is a tool called EasyEDA, and the target product will be an LED driver using AL8805 IC. Before going into the design, let me briefly introduce you about the AL8805. AL8805 is a component that supplies a constant current to drive the LED. There are 5 pins with the SOT25 package. V-in and GND pins are for power supply. The set pin detects the voltage and turns on and off the switch inside the SW pin. The control pin is for dimming control, and it can perform dimming control with DC level or PWM duty cycle. Let me explain the operation by referring to the reference circuit in the AL8805 datasheet. When the power is applied, the switch inside the SW is turned on, and the current flows through the SW pin to the ground through R1, LED, and L1. When the switch is kept on, the current flowing through the L1 inductor rises, resulting in increase of the voltage drop in R1. When the voltage drop of R1 increases, it is detected through the set pin and the internal switch is turned off. When the switch is off, the current is supplied from the inductor to the LED through D1 diode and R1, and the current flowing through R1 decreases over time. As a result, the voltage drop decreases, and the switch in the SW pin turns on again, and by this way, the amount of current supplied to the LED can be adjusted. Therefore, when the resistance of R1 increases, the LED current decreases. Conversely, when the resistance of R1 decreases, the LED current increases. The relationship between R1 and LED current is as follows. Therefore, to supply 330 mA of current, 300 mΩ should be used. To supply the maximum current of 1 ampere, 100 mΩ should be used. Now that we have checked the basic operation, we will check the required specifications for each part. First is the input and output capacitors C1 and C2. The input voltage range of AL8805 is 6 to 36 volts, so the voltage rating of the capacitor should be about 50 volts. Also, as mentioned in the datasheet, it is recommended to use a capacitance of 2.2 microfarad or higher in grade X5R or X7R. Therefore, we will use a capacitance of 10 microfarad, a voltage rating of 50 volts, and X7R type capacitor. The next are the parts through which the current supplied to the LED flows, and these parts should be capable of handling a maximum current of 1 ampere. The maximum amount of current for R1 varies depending on the resistance value and has the following relationship. Therefore, if you consider supplying up to 1 ampere, the power rating of R1 should be over 0.1 watt. Considering the margin according to the temperature, a resistor with a power rating of 0.25 watt will be a good choice. For the resistance, I will use a 300 mΩ resistor to supply 333 mA current. Next is the L1 inductor. The voltage across the inductor and the current flowing through it have the following relationship. Therefore, when the inductance is large, the current changes slowly, and when the inductance is small, the current changes rapidly. Therefore, the switching frequency of AL8805 varies depending on the inductance value, but in this LED driver application, the switching frequency is not a critical factor, so 33 microhenry will be used as introduced in the datasheet. Considering a maximum current flow of 1 ampere, we will use an inductor with a rated current of 1.2 ampere. Next is the diode. This diode should also carry a current of up to 1 ampere, so we need to use a diode with an average forward current of 1 ampere or more. Also, since the maximum input voltage is 36 volts, you should use a diode with a reverse voltage of 36 volts or higher. Therefore, we will use a Schottky diode for fast switching and minimum voltage drop, with an average forward current of 2 ampere and a reverse voltage of 40 volts. You can include the LEDs in the design, but just by adding a connector, you can provide more flexibility in how the LEDs are connected. For that purpose, I will add a 2-pin header connector to the LED output terminal. Also, for input supply and dimming control, Let's add a 3-pin header connector. This is the summary of the parts to be used and their specifications. Using this table as a reference, let's design the circuit with EasyEDA. First, log in to EasyEDA. Click on EasyEDA Designer at the top. When you log in, the projects you have worked on appears in the left menu. I will create a new project for demonstration purposes. Click File, New, Project and type the title. I will name it LED Driver 3. And click Save. Then, a window appears where you can draw the circuit. If you click on EELIB from the menu on the left, you will find several basic elements such as VCC, GND, and parts such as RLC. You can use the parts from this menu, but I recommend you to add parts from the library menu shown below. The parts from the library has a corresponding drawing data, which can be used when designing the PCB. Click on Library and then LCSC Electronics to find the part. You can filter the required parts by selecting the specification from this window. You can also check the image, price and availability of the part. As a start, I will add capacitors first. Select capacitor from the category, capacitance, 10 microfarad and voltage rating is 50 volts. Then click Apply Filter. There are 179 parts which matches the criteria. Let's add the class X7R for the filter. Among the 33 parts, the second part here seems reasonable. Click on the manufacturer part number to check the specifications in more detail. If you look at the description below, you can confirm that the specifications is correct. Go back to the circuit and press the place button next to this part. Then you can see the circuit symbol on the left and the PCB library on the right. Click the place button at the bottom and click the left mouse button where you want to locate in the circuit. I will place 2 capacitors each for input and output. Let's add the rest of the parts this way. We have now placed all the parts on the schematic. Now add VCC and GND and the wiring. VCC and GND can be selected from the symbols of EELIB menu or from the wiring tool above. After placing VCC and GND in the wiring tool, select the wire tool for wiring. When you select the wire tool, a cross shape appears at the location of the cursor, and in this state, click the left mouse button. Then click again on the desired location to complete the connection. Let's complete the wiring a little faster. There is a useful tool we can use, when wiring gets a little bit messy, is the net port tool shown here. Even when the wires are not physically connected, the wires are actually connected if the same labels are used. Now the circuit is complete. If you click Save in the upper left corner, you can see that a new sheet has been created in the project. Then, let's do the PCB design with the completed circuit. Click Design. Convert Schematic to PCB from the top menu. In the window opened, you can set the number of layers, the board outline, and the size of the PCB. I will create the PCB with the width to 40 mm and height to 10 mm. The PCB size can be modified during the design, whenever you feel it necessary. The purple box is the PCB area, and we need to place all the parts inside this area. Now, let's place it. Place the connector first. We can rotate the component the same way as when drawing the schematic. The connections between the parts are marked with lines, but if it isn't clear of the connections, zoom in on the part and the net name is visible on the pad like this. We can also take a look at the circuit for a reference. Now, we need to make connections between the components. In general, the connection of VCC and GND should be done by a plane, for a low impedance path. VCC is connected with C1, U1, D1, and R1 through pin 1 of H1. So it would be nice to make a plane connecting these pins. Also, the path connecting pin 1 of U1, D1, and L1 is also the part where the main power passes, so I will connect it as a plane. To draw the plane, we have two options, copper area and solid region. I will use solid region for drawing the plane for VCC and for the main current paths. Click the left mouse button continuously to form an area where you want to place the plane. The plane region is visible by the red line. When the area selection is complete, right-click to complete the plane. Now I will draw the rest of the plane in the same way. Now let's connect the signal lines. The signal between the set pin of U1 and R1 has no direct path for connecting each other. In this case, we need to route the signal through the via. We can add a via manually by selecting it in the PCB tool, but vias can be added automatically when wiring across layers. Select the track for wiring in the PCB tool, click the pin of U1 and move it to the side, and you can see the trace is created. Click the left mouse button at an appropriate location and move to the bottom layer. The trace will then turn blue, indicating that it is being routed on the bottom layer. We can freely route the signal, since there is nothing in the bottom layer. Click the empty space between the pads of R1, select the top layer for connection with R1, and connect with the pads of R1. When we complete the wiring, you can see that the vias are automatically created where we switched the layers. Let's connect the dimming control signal in the same way. The H1 part is a through-hole type, so it can be wired directly from the bottom layer. Select the bottom layer and route accordingly. Click near the pin of U1 and finish the connection to the top layer. Now, for the ground connection, I will use the copper area tool. If you select the copper area in the PCB tool, you can choose the net for which to apply the copper. The copper area tool is a very convenient tool, which automatically connects the related nets within the plane area you select. After selecting copper area tool, draw a box for the entire PCB area to apply a ground layer to the whole PCB as well as the part where the ground should be connected. If you click the right mouse button after designating the area, you can see the ground plane is created like this. Similarly, we will add a ground plane to the bottom layer. Now, let's move and rotate the silk of the top layer. Next, we will add silk for identification of the input and output pins. Since the top layer is lacking of real estate, I will add the silk to the bottom layer. Select text in the PCB tool. Reduce the size a little, double-click the text to modify it, and place it in the desired location. Copy and paste the text for other pins. And align the letters. Finally, let's add an image in the PCB to make it your own. I will put the Gemsung logo. After clicking the image in the PCB tool, you can select the image file. The image needs to be resized. Put the image where you want. And it's done. After saving, you can see that a new PCB file is created in the Design Manager. For the next step, I will show you how to order the PCB. Click on the PCB fabrication file in the menu, and DRC check. If there is no problem, you can see the final image of the PCB. You can select the options here, but some options selected here may not be reflected in the price, so I prefer selecting the options later, before ordering the PCB. Let's select lead-free. The price increases a little bit, but still very low. Click the Order button here to place an order to the JLC PCB. The Gerber file is automatically transferred to JLC PCB, so no additional action is required. Here, change the options you want. Red, yellow and white are quite expensive. So let's select black, click Save to Cart. Check out, and enter the shipping information, and make the payment. In my case, the delivery was done within 2 weeks. Additionally, I will introduce how to order the parts to be assembled on the PCB. Going back to EasyEDA, select BOM and click Export BOM to download the CSV file. Open this file. Remove the columns except the supplier part and manufacturer part and save. Next, go to the LCSC Electronics homepage. Log in, and click the Upload Part List. If you drop the CSV file saved earlier, the part list appears. Select Manufacturer Part Number and LCSC Part Number as the column name, and click Next to check the availability and MOQ, the minimum order quantity. Enter the quantity for each parts. Check the price, and proceed the order with Add to Cart. Let's compare the custom product versus the reference commercial product. Comparing the price of the Picobuck with 3 LED drivers and the custom product, the Picobuck is $15.90, while the custom product is $8.34, which is only half the price. If we made the driver to support 3 LED drivers in one PCB, it would have been much cheaper. Another advantage over the commercial product is we can add more flexibility to the custom product. Conversely, if you want, you can also create a product that is optimized for a specific application. This is the PCB manufactured from JLC PCB. A very neat black-colored PCB. And in the bottom side, there is the Gemsung logo we've added as a final touch. Now for the demo. This is the configuration for testing the LED driver we have designed. The potentiometer sets the voltage level, which is read by the Arduino analog pin. The Arduino then generates a PWM signal according to the level of the analog input for dimming control. When we apply the power, you can see the LEDs are brightly lighted up. Dimming control using PWM is also working well. Feel free to download the source code in the comment below, used for this demo for the Arduino Uno for PWM dimming control. And, a video introducing the Picobuck LED driver is also available for your reference. That's it for today. Thank you for watching. See you in the next video.